All right, so today's lesson is on the characteristics of function graphs. We're going to talk about what some of the attributes of a function and how they are related to the function's graph. And today's mathematical practice is looking for structure. So what we're going to be talking about is how well the math, if I can get this to right, how well the math fits together. Sorry, there we go. How well the math fits together, and basically how it's connected to one another. So that's really what structure is about. So the structure that we're talking about, yesterday we looked at domain and range. We're going to see some other attributes of a graph that are connected to domain and range. So we're going to start by identifying the attributes of a function from its graph. We're going to do the explore together again. Eventually when Mrs. Ballard comes back, then you guys will be doing more of the explore on your own. You can identify several attributes of a function by analyzing its graph. For instance, the graph shown, you can see that the function's domain is 0 to 11. So if we look at the x values, it starts at 0 and it ends at 11. And then its range is from -1, so the lowest y value was -1 and the highest is 1. We talked about all of that yesterday, so I'm going to erase those markings. So now we're supposed to use the graph to explore the function's other attributes. In part A here, we're supposed to find the values of the function of the interval from 1 to 3. So we're looking from 1 to 3 on the graph. And we need to decide if they're positive or negative. And this is a really, really excellent skill to have for AP Calculus. So understanding where it's positive and negative on a graph. So because the values are above the x-axis, we know that those y values are positive. Okay, and when they talk about the word value, they're talking about specifically y. The values of the function on the interval from 8 to 9. So from 8 to 9. And they want to know if they're positive or negative. So those values are below the x-axis, so that would make those values negative. So notice, we're not looking at whether the graph is going up or going down. We're looking at where it's located, where the y value is located, either above the axis or below the axis. Now we're going to talk about increasing and decreasing. Again, this is a good idea to get out the colored pencils, and you're going to underline what our definitions are. A function is increasing, so I'd probably underline that on an interval of f of x of 1 is less than f of x of 2, when x sub 1 is less than x sub 2, for any of x values on the graph, or any x values x sub 1, x sub 2 in the interval. So what on earth does all of that mean? It basically means the graph of the function is increasing on an interval as it rises from left to right on that interval. Basically, they're saying that the y value, as the x values get bigger, so that's what this means, is the x values get bigger, the y values also get bigger. So it's basically going up from left to right. Similarly, a function is decreasing on an interval if, so we want to probably underline that, if the y value at x sub 1 is greater than the y value of x sub 2 when the x values increase for any x values x sub 1 and x sub 2 on the interval. And basically decreasing and interval falls from left to right on that interval. So again, as your x values are getting bigger and bigger and bigger across the graph, the y values are getting smaller. So we're going to identify the increasing and decreasing on this graph that we have. So the given function is increasing or decreasing on the interval from 2 to 4. So if we look from 2 to 4, it looks like it's going down, so therefore it is decreasing. The y values are getting smaller. The function is increasing or decreasing from 4 to 6. All right, let me erase kind of what I scribbled on my graph there. All right, from 4 to 6, it definitely looks like it's going up, so we would say that it is increasing. For the points x sub 1, f of x sub 1, and x sub 2, f of x sub 2 on the graph, graph of a function, the average rate of change of the function is the ratio of the change in function values when we subtract our y values to the change in x values when we subtract our x values. All right, so we're going to underline that. Average rate of change of the function is the ratio. Okay, and remember, a ratio is just a fraction. Okay, For a linear function, the rate of change is a constant and represents the slope. So you might want to underline linear and represents the slope. So all we're really going to do is calculate the slope of a line here. So it wants us to, was the given function's average rate of change on the interval from 0 to 2. So what I need to figure out is I need to figure out what the function value is at f of 2 minus f of 0 over 2 minus 0. So I'm actually going to just go to where that y, to try to read that y value off the graph. So I'm going to go to where x equals 2. And I'm going to read that that y value right there is a 1. And then I'm going to go to where x equals 0. And the y value where x equals 0 is a negative 1. And then 2 minus 0 is 2. A double negative goes positive, so I've got 2 over 2, which is going to equal 1 for the average rate of change. All right, so we still have the same graph, a lot more attributes about it here. A function may change from increasing to decreasing or decreasing to increasing at turning points. The value of f of x at a point where a function changes from increasing to decreasing is a maximum value. So where you go from increasing to decreasing, you have a maximum. A maximum value occurs at a point that appears higher than all the nearby points of the graph of the function. So we know a maximum is higher. Similarly, the value of f of x at a point where a function changes from decreasing to increasing is a minimum. A minimum value occurs at a point that is lower than all the nearby points of the function. If the graph of the function has an endpoint, the value of f of x at that point is considered maximum or minimum value of the function. So an endpoint can be the maximum or minimum of the function if the point is higher or lower respectively than all nearby points. All right, so the next thing we're going to talk about is how many points we are increasing or changing from increasing to decreasing at. So how many points does the function change from increasing to decreasing? So increasing to decreasing, there's 1. Increasing to decreasing, 2. Increasing to decreasing, it looks like 3. What is the function's value at these points? Remember, value, we're talking about what is the y at those points. In this case, they all happen to have the same y value. If I looked across at the y value, it is 1. Okay, I'm going to erase on my graph. Okay, so we're going to look now again at how many points does the function change from decreasing to increasing. So decreasing to increasing, there's 1. Decreasing to increasing, there's 2. And again, they want the value, the y value at those points. So if I read that y value off the graph, it's negative 1. All right, now this one's really important. Zeros come up quite a bit. A zero of a function is a value for x for which the y or f of x equals 0. Okay, they're also known as x-intercepts. They're also known as, eventually we'll get to, roots. Okay. So zeros, x-intercepts, and roots are all the same thing. So it's asking us how many x-intercepts does the graph of the function have. So I'm going to count 1, 2, 3, 4, 5, 6. So it looks like there are 6 zeros or x-intercepts. It wants us to identify the zeros of the function. So we're just going to make a list of all those numbers where we circled where it crossed the x-axis. So 1, 3, 5, 7, 9, and 11. All right, so we're supposed to identify 3 different intervals that have the same average rate of change and state what the rate of change is. So remember, average rate of change, another word for that, for linear, is looking at the slope. So if I went back and I looked at that graph and I looked at where the slope was the same, I'm going to erase these guys here. So I need to find 3 intervals where the slope is the same on that graph. So if I look at the slope, I'm looking for kind of parallel slopes. I know that the slope is the same right there, there, and there. Or I could use those 3. Okay, so I'm going to go back with the blue ones. Doesn't matter which ones I use. So it looks like I've got, remember we're listing our x values, 0 to 2, 4 to 6, and 8 to 10. So, and they say they don't state any particular type of notation. I'm looking at the book answer. They use the set notation, but I like interval notation better, so I'm going to use the interval notation. So we said that the first one is from 0 to 2. Oh, and we should be using brackets. So 0 to 2 brackets. 4 to 6 with brackets. So see, here's using the structure that we used yesterday. And 8 to 10. Now, you have a choice of how you decide what the actual average rate of change is. We could count our slope triangle, okay? We also could go ahead and do our slope calculation. Remember where we take our y values and we subtract them and take our x values and subtract them. So I'm going to go ahead and use the y values and the x values. I'm going to use these 2 points right here. So I know my y values are -1 minus that 1. And then my x values would be 0 minus the 2. So I end up with -2 over -2, which goes +1. So we know that our average rate of change, and you could have just shown that work on these lines here, equals 1. So our second discussion problem is, if a function is increasing on an interval, what can you say about its average rate of change on that interval? So if I think about where it's increasing, okay, if it's increasing, I'm going to erase on my graph again. All right, so if it's increasing in general, we know that it has what kind of a slope does it have? It looks like it has a positive slope. So if it's an increasing average rate of change, it has a positive slope. If it would have been a decreasing average rate of change, it would be a negative slope. So that's probably what I would say. So let's go ahead and write that down. The function is increasing. What can you say about its average rate of change on the interval? So we would say the average rate of change is positive. That says positive. Because B/C is because it said we had to say why. Because as the x values increase, that says increase, the y values also increase. I apologize for my handwriting. I'm hoping to get a different pen that makes it a little bit better on the next few lessons. So average rate of change is positive because as the x values increase, the y values also increase. All right, so I've got good news for you. We're only going to do explain 1 today. We're not going to do explain 2 at all. We're going to just skip over it, okay? So we're going to try to understand kind of what they've done in this example, and then we're going to do another example or 2 together, and then that's it for the day. So we're supposed to sketch a function's graph from a verbal description. So by understanding the attributes of a function, you can sketch a graph from a verbal description. So the instructions say sketch a graph of the following verbal descriptions. So it says Lyme disease is a bacterial infection transmitted to humans by ticks. When an infected tick bites a human, the probability of transmission of a function of the time since the tick attached itself to the skin. During the first 24 hours, the probability is 0. So 24 hours, 0%. During the next 24-hour periods, so next 3 24-hour periods, rate of change is always positive, but is much greater for the middle period than the other 2 periods. After 96 hours, it's almost 100%. Sketch the graph of the function for the probability of the transmission. So they're going to kind of step us through that sketching. Identify the axes and scales. So they labeled their x-axis as the hours, and then they labeled their y-axis as the percent probability. And they say the hours are going to run from 0 to 96. And then the y-axis is going to go from 0 to 100. So identifying key intervals. And so it was talking about 24-hour increments in there. So our first interval is from 0 to 24, 24 to 48, 48 to 72, 72 to 96, and 96 to 120. We're going in 24-hour intervals. So now we're supposed to sketch the graph of the function. Draw a horizontal segment from y equals 0 for the first 24-hour period, and that came from here. The first 24 hours, the percent chance is 0. So we're going to draw a horizontal. And notice they did every other mark was their 24-hour period. The function increases over the next 3 hours, with the middle interval having the greatest increase or the steepest slope. So basically, they kind of made some. They didn't guess, but they made some educated guess markings. So they put a mark a little bit above an increase. In the middle, in that next 24-hour period, is a greater increase, and then the slope decreased again a little bit. So that's where they got the next 3 markings from. After 96 hours, the graph is nearly horizontal. So they did something that was not quite horizontal, but really, really close to horizontal for that last little bit. And they did it up at 100% because that's what the problem said here. All right, so now we're going to try this again. Okay, on our own, we get to actually draw the graph ourselves. So the incidence of a disease is the rate at which the disease occurs in a population. It is calculated by dividing the number of new cases of a disease in a given time period, typically a year, by the size of the population. To avoid small decimal numbers, the rate is often expressed in terms of a large number of people than a single person. For instance, the incidence of measles in the United States in 1974 was about 10 cases per 100,000 people. So that's how they notice their labels here, cases per 100,000 people. It said 74 was 10 cases per 100,000. You'll notice that the graph is numbered in years instead of them saying that the year numbers. So 74 is year 0, 75 is year 1, and so on, 76, 77, 78, 79, 80. So you got to kind of be careful about that and translate it because they labeled it years since 1974. So it says that from 74 to 80, there are drastic fluctuations in the incidence of measles in the United States. In 75, there was a slight increase from 74. So I'm underlining the important parts of this problem. The next 2 years saw a substantial increase in the incidence that reached, we got a maximum value in 77 of 26 cases per 100,000 people. From 77 to 79, the incidence fell to about 5 cases per 100,000. So that might be some kind of minimum value that we could mark on there. The incidence fell much faster from 77 to 78 than from 78 to 79. So faster from 77 to 78 than 77 to 79. Finally, from 79 to 80, the incidence stayed about the same. Okay. So it says identify the axes and scales. So the x-axis will represent the time by years and will run from 0 to, well, they are stopping it at 6 because they talk about 1980 and it started in 74. The y-axis will measure the incidence of measles. Sorry, I'm not fitting it all in there. Measles. Per 100,000 people will run from 0 to 30. Okay. Now, I'm sorry I lost all my markings that I had underlined there. Identify key intervals. The intervals are 1-year increments from, and our graph is marked in 0 to 6, but remember that translates from 74 to 80, really. But we want this, they're looking for the 0 to 6. We're going to sketch the graph of the function. The first point on the graph is, and it's said right in here, 10 for that 1974, which is year 0. So it's going to be 0, 10. So I'm going to mark that point on the graph. Sorry, my pen does not mark points very well. It erased it. Okay. The graph slightly, and we have to decide if it rises or falls from 0 to 1. So let's talk about that again. So it's 75. There was a slight increase. So that means it's going to rise from 0 to 1. From 1 to 3, the graph rises or falls, so we have to look at that. Next 2 years saw a substantial increase, maximum at 26. So it rises again to a max of 26. Okay, and I could go ahead and mark that in. So from 1 to 3, I know it's up here at 26. Sorry, I know it's a really small dot. Then the graph rises or falls steeply from 3 to 4. So let's look at the next one. From 77, the incidence fell to 5 cases per 100,000. So we know it's going to fall. And that goes, oops, I lost my dot, didn't I? So 3 was up here at 26. Let's see if I can make it bigger. That's obnoxiously bigger. And it's going to come all the way down here to 4. Okay. And then it rises and falls less steeply from 4 to 5. So it says, let's look at it. It says that the incidence fell much faster from 77 to 78 than 78 to 79. So we're saying it's going to fall again. Oops, and I lost my dots again. What's going on? So there's my 1 dot, and then it should be falling again a little less steeply. From 4 to 5. 5 cases per 100,000. So here, and then it basically, and then the graph is horizontal basically from 5 to 6. So what I want to do is try to sketch that in there. The first one said it increased a little bit, then it increases steeply, then it decreases, then it decreased a little bit more, and then it was finally horizontal. And I know mine is not pretty to read right now. All right, we've got one more here. Oh, we got to reflect a little bit. So in part B, the graph is horizontal from 79 to 80. What can you say about the rate of change for that interval? If it's horizontal, the rate of change is 0, right? It's not changing. So we'd say the rate of change is 0. Of change is 0. All right, we got one more here to deal with, okay? So we don't have to go through all those details. We can probably just sketch it from as we're reading through the problem. The grocery store stocks shelves with 100 cartons of strawberries before the store opens. So we know that we're already at our initial value there. We're at our initial X. We're already up here at 100, okay? For the first 3 hours, the store is open. And notice it's hours opening on the X and cartons of strawberries on the Y. For the first 3 hours the store is open, the store sells 20 cartons per hour. So per hour means we're selling 80 in the first, or we're dropping down to 80 in the first hour. Sorry, my dots disappear when I draw it. And then we're dropping to 60, and then we're dropping to 40 within the first 3 hours. Okay, so fairly steady decrease. Over the next 2 hours, no cartons are sold. So for the next 2 hours, we're going to go horizontal because they have a lull in business. Nobody's shopping for strawberries. Sorry, my dots keep disappearing. All right, and then the store then restocks 10 cartons each hour for the next 2 hours. All right, so actually I'm going to draw my lines in there. So I've got a line going down. I know I've got a horizontal there. So for the next 2 hours, no cartons are sold, the store restocks 10 cartons each for the next 2 hours. So we're going to put 10 cartons for the next 2 hours. So I'm only going up by 10, a steady increase. And there's my line. And then in the final hour, the store is open. 30 cartons are sold. So I'm going to drop from here all the way down to, I'm going to go down 3 hash marks, right? Because I've got to get rid of 30 more cartons. And there's my sketch. Now, I said we were going to skip the, explain 2. So you guys need to flip to page 23. And that's where the elaborate is. So you're going to do elaborate 7. You're going to do elaborate 8. You get to skip elaborate 9 because we didn't cover that. And then I want you to go ahead and do elaborate 10. And that's how you're going to finish to get your class points for the day.